Hey, good afternoon, everyone. Thanks for joining us today. Like Justin mentioned, my name is Ray Kerrigan. I'm the energy manager from Efficiency Nova Scotia with Dalhousie University, and with me is Ted Laux from MCW Custom Energy Solutions. Work together between Dalhousie and MCW to develop this project, which is now underway. So today we're going to talk about the Killam Library Deep Energy Retrofit. So our agenda for today will be to start with an introduction and purpose, kind of how we got to this project in the first place. I'll explain a little bit about the building, give some more context around what we're working with. We'll get into the project itself at a high level, and then at a deeper level for some of the more interesting measures. We'll cover the implementation process and what we had to go through to make sure this project works. Then we'll finish off with expected results, benefits, and next steps for Dalhousie. So where this project really comes from is from planning. So Dalhousie has two plans that we really draw from for this idea. And that's the Energy and Green Buildings Plan, which was updated last year, as well as the Climate Change Plan. So the actions required, and to meet those goals requires big action, and a deep energy retrofit is one of the ways to achieve a lot of energy and greenhouse gas savings in a relatively short period of time, and really helps drive towards our goals of becoming 50% reduced greenhouse gas by 2030, all the way up to carbon neutrality by 2050. And how this relates to the actual library itself and what we're going to do is improve the building and energy and water efficiency, of course, and therefore reduce the greenhouse gases, implement some facilities renewal, which basically just means, equipment near or past its useful life that was deferred. Maintenance, it's a great opportunity while you're in the building, tearing it apart, to also upgrade a lot of the equipment. And overall, our big focus for Dalhousie, being a university, very student-focused, is making sure its students and faculty are comfortable. And this is easily the most frequented space on the whole university. So improving occupant comfort was a key priority for Dalhousie as well. And we achieve this through this deep energy retrofit program. So here's a photo of the Killam Library on the outside. It's brutalist architecture, so it's up for debate if you like that or not, but it is a well-designed building. And this is the front south-facing wall. That is the main entrance to the building. So it's the third largest building on Dalhousie. It comes in at 250,000 square feet. It's in the top 5 most energy and carbon intensive buildings on campus, so it makes it an obvious target for something like this. And this comes after 2 successful other deep energy retrofits at the Tupper building on the Carleton campus, which houses our medical school, and the Life Science Center, a large lab building on the Slidley campus as well. So after the successful completion of that, this is the next logical step. And also adding to this is that the building is quite old. It's 52 years old. So although there have been upgrades throughout the years, the whole building approach really wasn't taken. So it was a great opportunity to do the study and see if it's worth pursuing further and larger upgrades through this deep energy retrofit. And just to give you a sense of, I'm sure many of you have gone to Dal or been at Dalhousie University before. But it's not just a conventional library that stores books. There's lots of study spaces. It's mixed use. There's computer labs, even food services in the atrium. So there's a lot of different needs that need to be considered when doing a performance contract. And another important thing to note is, like I mentioned, it's a very busy building. It operates typically between 8 a.m. and 11 p.m., but quite often the hours are extended to accommodate students' needs, like exam times, for example, or other department needs. So just something to keep in mind as we go through the details of this project. And here's an aerial view of the library. So like I mentioned, it's situated on Halifax's Studley campus, the main campus in Halifax. It's between the chemistry building to the west, and to the north, the Howe Hall residence. So it's very centrally located on campus, and sees a lot of traffic. You can see the rooftop. There's an enclosure over what used to be an open to air, but we, in the 90s, Dalhousie covered that to make it more usable space that year round, and that's what where currently the food services and large atrium is situated.
Ray, are those solar panels?
They are not solar panels, those are windows. Great question. And I know everyone here is probably interested in the energy side of things, of course. So the utilities, it costs the university close to $1 million a year to just in utility costs, and this works out to be over 10 equivalent gigawatt hours of energy being consumed. And if you factor in the square footage of the building, that 250,000, it brings us to a EUI, or energy use intensity, of 44 equivalent kilowatt hours per square foot, which is definitely a prime target for improvement. Electricity makes up 29% of the energy and 46% of the cost, and steam is largely the rest, with making up 63% and 47% of the cost. In terms of carbon intensity, so the building emits over 4,000 tons of CO2 equivalent annually. So it's a big goal with this project to reduce that, of course. And much of that, or almost half, is from the electricity alone. So there's only so much we can do with that, but Dalhousie still should maintain the focus as the grid gets cleaner. But then another large part of the carbon output is from the chilled water and steam systems. So the building is fed. I should mention that the building is fed from a central plant that's located on Sexton campus that supplies steam and/or hot water throughout all our Halifax campuses. And on the electricity side, our campus is actually very well sub-metered. We use ion meters from Schneider, and so the main electricity is fed on this campus at the Wealth and Law building, and then it's distributed throughout all the other various buildings. And it's great to have such reliable sub-metering, because then we're able to separate out this building and rely on the electricity consumption profile. And as you can see, it's very steady month to month, which definitely implies there's probably room for improvement, just even at face value. And we'll touch on why that is as Ted gets into the more details on the measures we're implementing. On the steam side, it follows a much more probably typical profile. So obviously in the winter and colder months, we're going to be using a lot more steam than in the summer. And we did normalize this with weather to make sure that is reading accurately, and it does fit quite well. So that gives us confidence going into a project like this, that at least we have a good baseline to work with and good data to work with. So a feasibility study was the first step after this project was conceived. So this came out with 26 broad improvements that were identified with various options that Dalhousie could go forward with. I just want to highlight that, of course, saving energy and carbon reduction is a key priority and key driver of this project, but it's not the only factor. Dalhousie, like I mentioned before, really has to take into consideration life safety and occupant comfort, amongst many other factors that need to be considered when making decisions. So it's not always an easy decision to just go with what saves the most energy. You do got to find that balance, especially when it comes down to costs, which everything always does. So we decided to go forward with a turnkey energy performance contract based on that feasibility study. And I just want to kind of give honorable mention to a few measures that we had unfortunately cut out. And that's the atrium entrance revitalization. You can kind of see that in the top corner there. The south wall transformation and solar PV, unfortunately, were not able to be included, but they were fully studied, so we can always return to those, should the funding come or should other opportunities come. So it's always good to have be armed with that information. And what did make it through is, so there's still a lot of fluorescent lighting throughout the building. So that's, even without an EPC, we know we had to change that. But that's of course going to be included in the overall project. And again, Ted will get into more detail on the more interesting measures to you folks. But we touched on the ventilation system, of course, so adding variable air volume, heat recovery, duct cleaning, and the building system. So converting, this is a big part, particularly for the carbon intensity, is converting from steam to hot water and making it a low temperature heat, hot water, which really helps, especially down the line as Dalhousie looks to further improve the campus energy intensity, and it gives the ability to tie in with a variety of potential clean solutions later on. With any of these projects comes a lot of control upgrades as well. So both to enable the technology we're putting into the building, but also to take advantage of maybe areas where the building was already weak in terms of being able to be controlled. And like tying back to the original, our climate plans and energy plan, water efficiency is a priority for Dal as well. So we also implementing measures that will reduce water use. And last but not least is, those windows we mentioned, there's a lot of gaps in there and needs refurbishment. And so not only will it be aesthetically better, but it will also hold more energy into the building. And I'm not going to get into too much detail on the cost, but I will share that the capital cost of the project came in close to $19 million. And we're funding this largely through a guaranteed utility savings payback period of 20 years. So basically, the risk is shifted away from the university, and we can use that as the model to pay back through energy savings. Another portion of the project is paid through facilities renewal funding. So as I mentioned, it's a great chance to upgrade a lot of the building systems while you're already tearing things out and into the ceilings and everywhere within the building. So that was a big contribution to our project as well, and also helped the payback of some energy saving measures. And last but not least is the rest was funded through grants and incentives, and it's a great chance for me to plug myself and colleagues at Efficiency Nova Scotia, because we're able to provide incentives for the electricity savings that this project should provide. And basically, in terms of financing, we just basically had to make it work with Dalhousie's limitations and the ability to move forward. So that's why we had to make some difficult decisions to cut out some measures and make those decisions in order to allow this project to go through, because certainly a project going through is better than no problem. So that's where we are. And quickly, the timeline. All I really want to get across here is that these projects can take a few years to really get off the ground. You do need to thoroughly think about everything. So not just the energy savings, like I mentioned, like the impacts to the building, how it will operate afterwards, the costs, you name it. There's lots to think about. So started with a feasibility study, identifying a large list of measures. Once Dalhousie knew the funding situation, we had to make decisions on what goes forward, what doesn't. And that ultimately led to an implementation agreement with our partner NCW to start construction that started earlier this year and should be completed by 2025. But measurement and verification, something really important to myself. It will be ongoing both through the construction phase and well after, again, tying back to that guaranteed savings model that's really needs to be relied on to pay for this project. So now I'm going to hand it over to Ted to dive in a little deeper on the actual measures we're planning on and currently implementing.
Yeah, hi there, Ted Laux. So it's late in the afternoon, and so hopefully everyone's still awake, and I'm glad everyone's still here. Justin is wide awake, so that's good. And you know, it's close to nap time, but hopefully everyone's still awake. So hopefully we've got a few stories that we can tell as we go through to see what we can do. Ray, in 2022, it looked awful in slide number 185 slides in a day. That in 2022, all we did was sort out funding and approvals, but the approval process, as some of you know with larger institutions, is a many steps to get to the approval. You have to go through the building committee, and then the facilities management, and then through the provost, and then through the VP admin, and then up to the board of governors. And each step along the way might have minor revisions as you go through. So by the time we got to the end of it, there were several revisions to the program as we got to the end, and as we went through the project. And Justin said 5 years because probably one of the other large buildings that uses a lot of energy is the chemistry building. And so we started along a path to look at the chemistry building, and that was a great one to do. We got partway down the road, and then they said, you know, what we really want is a new building. And it's just like, okay, well, that doesn't quite fit into the energy performance contract model, but we did have we looked at that and looked at several ways to create swing space for them. So we went down that road for a couple of years, and they're on the road towards a new building. If anyone has any spare change that they would like to contribute, you can be a funder and maybe get your name on one of the buildings there. In terms of the building systems within the library, it is a 5-story building with a basement. It's connected through a tunnel to the central services building, to all of the main steam and chilled water. It's quite simple when you look at it in my simple little hand-drawn sketch, because there's only 2 air handling units in the building. There's one at the top end of the building in the 5th floor that does floors 2, 3, 4, 5, and there's one in the basement that does the basement and the 1st floor. So look at the size of the units. The first one, DD1, even though it's at the top, DD1's at the top, 120,000 CFM, 120,000 CFM. Typical unit is like 25,000 CFM. So these are they have 2 75 horsepower supply fans. They have 2 return fans on them as well. High pressure as well, because you're feeding down through the system to an old 50-year-old dual duct terminal that has high static, has big springs within them. So it takes a lot of energy to move the springs, to control when the springs aren't jammed, so that you get to the point where you can't even control the hot deck versus the cold deck air in the first place. So lots of interesting things. So you got 75,000 in the lower floor. It does have a data center with 6 computer room air conditioning units that are recently upgraded, and so there is they go over to the adjacent building, the chemistry building, where the heat is rejected. We were looking at tying into those systems, but it looks like a better opportunity if you tie it into the chemistry building, and it was recently upgraded, so it kind of was not part of the scope of the work. Dalhousie said, let's look at that later. So that's good. On the central steam, so you do have high pressure steam coming from the central services building. It does all of the buildings on the Studley campus, and then it does a steam to hot water conversion, so it feeds a number of buildings down at the Sexton campus, which is the architecture and engineering campus for Dalhousie in the downtown part of Halifax. Recently, there was a steam to hot water conversion in Howe Hall Residence, and so the Howe Hall Residence is the next building over through the tunnel on the steam system side, so it uses the basement of the Killam Library to do that conversion that was done during the pandemic period. So it's a great time for the university to address that infrastructure when there was very few, if any, students in the Howe Hall Res. To get that one converted from steam to hot water, which is part of the overall goal of Dalhousie. So very interesting building. On the lighting side, there's a mix of fluorescent and LEDs, and it's like a lesson in history. Everywhere you go in the building, you know, you can find stuff that is 50 years old, right from its original design and construction. The lighting is on 24 hours a day because they used to have switching, but through 50 years of electrical contractors tying in different things, they can no longer isolate the circuits without turning off someone's computer or someone's kettle if you turn off the light switch. So here's the best thing is that I had the good fortune of being able to tour through this building at nighttime with the famous energy engineer of the year. So we spent a good night, couple of nights looking through the building, and so I now can say that I did that with the energy engineer of the year. So that was fantastic. Yeah, so it goes. There's some we even found T12s in the building, so there's lots of interesting stuff. Lots of stacks, so lights within all the stacks. There's lots of interesting things to do. So based on race good information about the utilities and all of the information, you begin to think about the opportunities about what you could do with this building. And first step, of course, you do the energy model. And so we use a program, Integrated Environmental Solutions, Virtual Environment, otherwise AEECE, where we developed a model. So on the top, you can see what comes out of AEECE. Oh no, the other way around. That comes out of Google Earth, and then that's our digital twin. And just like we talked about this morning, parametric analysis to look at all the various improvements. Which one do you do first? Which one do you do second? Which one do you do third? And then the project manager for Dalhousie says, what if you don't do this one? What if you do a different combination of them? And then we come up with some other arrangement. So the output, okay, so here's an image only energy modelers could love. Like, look at that. But I annotated it a bit just so you can see what everything is. But that's the kind of output that you get from some of these energy modeling programs. It's not the best, but it has all the components in there. So there's your air handling system, the dual duct air handler, where you go through the supply fans and the heating coils and cooling coils. You go downstream to each of the floors. You got your dual duct air terminals, return air. There's exhaust air. There's building exhaust for a variety of different things: washrooms, elevator machine rooms, general exhaust. We don't have. And maybe somewhere in there is the atrium and dealing with the atrium and its pressure issues. So we can get to that. And so here's another beautiful looking report that comes out of IES that only a modeler could love. The top one shows that it was a constant volume unit, so it blasts away at 120,000 CFM constantly, modulating between how much hot deck and how much cold deck you get, but always delivering the same amount of air to each of the spaces, when that wouldn't be a modern conventional design. So it's actually quite nice because your dual duct terminals do provide you cooling and heating into all the spaces at all the times. So you can put adjustments on each one of those to get you to the post retrofit. So you can see that all the white space below there, below the big blue line that shows your energy savings as well as your peak is reduced by 20–25%, and then it shuts off. That the fact it drops to 0 every time is because it shuts off at night. So just a bit more information about each of the major improvements. So the dual duct air VAV conversion. So with the air handling units, they're 50 years old. They're rugged, they're strong, they were built like tanks back in their day, but they show their signs of wear. So just look at the risers on the stairs. This unit is like 16 feet tall. It's about 16 feet tall, 16 feet wide. So it's a huge thing. It's 120,000 CFM. So we looked at a couple of different approaches, but including full replacement of the unit. We did an analysis of replacement versus refurbishment of the unit. And so we looked at refurbishing the unit. Dalhousie's had success with some of their other buildings to do exactly this at their arts center, in a couple of other facilities, the Life Sciences Center. So dampers, coils, filters, and then you can fix up the fans, refurbish them. There's VFDs on the fans, controls upgrade. And so when you do this, you won't have any ventilation. So we have a summer shutdown plan for 2024. A couple more pictures just of the inside of the unit. You can see that it is in reasonably good shape, but some of the components within it are showing signs of wear. So we can get that all fixed up and looking good. On the right-hand side is the arrangement of the penthouse, the 5th floor dual duct system. You can see the outside air coming in from the left. It has recirculating air from the top and the bottom, goes through the filters into the 2 fans, pressurization on the right-hand side. On the right-hand side, where it either goes to your hot deck heating coils or your cold deck cooling coils. And then there's a big box on the lower right-hand side, which is a new exhaust air air handling unit, side stream, which we'll tell you about in a minute. On the dual duct VAV conversion, so that's what happens up in the penthouse. Down in the spaces, the dual duct VAV conversions are the boxes that mix the hot deck warm air and the cold deck cold air through some dampers to put out whatever temperature you need within the space. This one is a nice example because there's, how many retrofits do you ever see that look like that where there's nothing in the ceiling? There's no pipes in the way, there's no other big ducts in the way, so this was a fortunate picture and a beautiful picture of a dual duct terminal that we were doing the retrofit on. You notice there's no ceiling in this area, and what we did in the ground floor in the first zone that we went to, we said, it needs a new ceiling, we're going to put in a new ceiling. By the way, we're going to harvest all of those linear metal ceiling components, the Paraline ceiling, to use in other parts of the facility. So we had about 5,000 square feet, 6,000 square feet, something like that, of ceiling that we can now harvest and use for other areas where, as you take down the Paraline ceiling to put in the new dual duct terminals, you're invariably going to bend one, it's going to crack, something's going to happen. We looked at the three different options: reuse with internal dampers, reuse with external dampers, or a brand new dual duct air terminal. We did decide on after analysis, the third one, the new dual duct terminals, for a full renewal. And so something like this, we are going to do it 475 times. So you just work your way through the building. The controls are great because we do have trim and respond on the hot deck and also on the cold deck, so that you can say, okay, so that you're only providing the temperature air that you need for whatever your worst case condition is. And so then we have the automation system that looks at all 475. They decide what's the worst condition, and then you only control to that. So in that way, you get your temperatures down as low as you can, and you do the same thing on the pressure side. The pressure reset from the fan upstairs only provides enough pressure so that you satisfy the worst case zone. So then you do this zone by zone, and then you end up, after 5 floors, you get $286,000 and 1,300 tons of greenhouse gases. Down in the basement, the steam to hot water conversion. So from the tunnel, there's existing steam that comes into the building. And so that space is used to have, okay, so there's steam in the air handling units and other steam converters, and so there's not a whole lot of pieces of equipment that use steam in the building, but those are the things that you gotta get addressed. And so we did put in hot water heat exchangers in the basement, and it's connected with the recent conversion at the adjacent buildings. Who remember slide 177 of today's presentation? Anyone? When Ray no one remembers? When Ray presented that picture, the aerial view that showed Howe Hall just to the north and chemistry off to the left. And so so Howe Hall is now connected, and so it comes back to here, and coincidentally, the load for Howe Hall and the load for Killam, Howe Hall complex, which includes Mona Campbell and a number of other facilities, is very close to being the exact same as what you have in Killam. So you put in for Howe Hall, you put in a duty and a standby heat exchanger, and then you need another one for Killam of exactly the same size. So you now only have to add one for Killam because you got duty, standby. So it's perfect. It works out great. And so the conversion to hot water aligns with Dalhousie's future conversion from steam to hot water, and through that improvement through that improvement, you end up with less savings than perhaps some of the other measures, but it gets you set up for what Dalhousie wants to do for overall steam to hot water across the campus and in all of their buildings. That's backwards, that's forwards. So schematically, if anyone can read those details, that would be good. But you can see down in the bottom left corner, the steam to hot water heat exchangers. And then on the top right, you can see the new heating and cooling coils. That's in the upper air handling unit. We didn't put circles around all of them. Remember the 3 blue circles on the diagonal in slide 196? Because we're going to talk about those next. The heat recovery chiller and the exhaust air heat recovery. So current condition at Killam Library. So you do have centralized exhaust. You have a dual duct air handling unit that needs heating and cooling. You have very large existing systems, and you only have a seasonal chilled water asset. So Dalhousie has a central chilled water system, but it's only in use from just before convocation, from May until October, and the other times of the year it's not available. So you only have 6 months of cooling, but there's, occasionally there's warm days in November, and everyone loves a nice warm day in March and in April. So what can you do in this application? You can take your exhaust air, you can put cooling coils in your exhaust air, so as to do the heat recovery. You can't do a wheel in a unit that's 15 feet by 15 feet. Like because then your energy wheel would be twice that size, and you just can't do it. You convert the whole system to low temperature hot water, low grade hot water, with the heat recovery chiller. So that's the essence of that guy. In schematic, another hand-drawn schematic, but interesting and useful to show a few things. So on the blue side, the chilled water side, you see the DD1 and the DD2. Those are the heating coils, the cooling coils that we're replacing. Beside those are the air handling unit 1 and air handling unit 2. Those are those little side stream exhaust air handling units. And through those units, we're bringing in all of the exhaust air. We're bringing in the elevator exhaust. We're bringing in general exhaust as well as washroom exhaust through those coils. And so you're cooling those guys down from indoor temperature, 22 degrees Celsius, down to something like 3, 4 near condensing on the discharge as you blow it out through the outside wall, and you recover all that heat. So now you've got the warm heat in your chilled water system. You can use that to put through a heat recovery chiller. Through the heat recovery chiller, you can take it over to the heating side and transfer that energy directly over to your heating coils. Now hot water heating coils, used to be steam, now hot water, and used in your building. The interesting thing about this is that you can tie and use most of the energy within the building most of the year without having to go back to the central plant. So on the right-hand side, you see the connection of the steam and the condensate to the central heating plant. So that's always there as a backup. At the same time, there are the green connections and the green highlighted in yellow connections, which are the chilled water that comes from the central plant. But there's also an interconnection, because in the future, Dalhousie is going to use their existing stranded chilled water asset that's not in use from October to May. Going to use that stranded asset in the wintertime for a low temperature hot water distribution system. So that's part of the future plans for Dalhousie. So now all of a sudden the building has chilled water available 12 months of the year. Pretty cool. Solar photovoltaic. Yeah, well, new products come along all the time, so we'll have a look at this again. But when we reviewed it, the snow loading on the roof, putting on roof-mounted solar would not meet the structural code requirements for snow load. So we said, okay, we can't go on the roof. What can we do? And we said, let's put it on the wall, because it is one of the best locations on campus. It's the very high profile. It probably has the most students walk by it every day, and it would be highly visible. So we looked at putting it in a band of solar along that top band, 40 kilowatts. To do so, we had to look at the structural integrity of that too. It's all precast panels, as you can see on the outside of the building. So we did have to do destructive testing to open up holes in the wall to look and to test the connection points onto the precast panels into the building structure, so that it was deemed that was acceptable to do those connections. So viable, but just kind of expensive. On the implementation side, oh my goodness, there's lots of the stories we could tell. We do have to do a phased approach as we go through the building. So we divide each floor into multiple zones, work with the users, with the library, to negotiate and discuss size of the zones, the timing that we can go into each space, and then we go into develop swing space and move out plans with the users where they're going to go for temporarily while they're not going to be in their spaces. Communications plan, so we do users meeting every 2 weeks. We have town hall meetings. There's notifications from campus planning and from the library to let the students and all the other users know, not just the 15 departments that we have to coordinate with. So this is the fun part. So you go to a town hall meeting, groups of this size, and you say, "Hello, library personnel. Thank you for coming to the meeting today. We're going to retrofit your building, and we're going to disrupt your life for 2 years. You're going to see people with hard hats and boots for 2 years in your building. We're going to fix up all this stuff, and at the end of the day, after 2 years, you're going to come back to your space, and you're not going to notice any difference at all, because we haven't done everything's behind the scenes. Everything's in the mechanical rooms and above the ceilings, and other than lighting retrofits, those are you're not going to see anything. However, all the users and the library, because they're great at compiling information and storing information, they have the list of all of the user complaints for the past 5 years. And so there's, the list goes on it's a spreadsheet that goes on for like 3 or 4 pages of issues. And it's invariably, you saw that there's no windows. Like the people who like low glazing percentages to get the building envelope performance would love this building, because there's just little skinny slivers of windows all around the building that, so there's no glass. And so people's complaints are, there's not enough outdoor light. It is dark in the building because it's older lighting. The ventilation is poor because you don't have good controls on all of the dual duct terminals. So invariably it's those, but every now and then you find a gem and you say, this room is always very, very cold. So you look at that and you say, can we do something and solve those problems? So those are the types of things that we've been working our way through. As you go through the implementation, you develop the takeover and turnover process and communications. And the drawing on the right-hand side shows the first floor and how far we're doing it. There's zoned areas. It's typical of each of the floors. We're shading in each of the zones as we progress through them. We're about to have, in about another week or so, about 80%, that next yellow one is going to be shaded in, leaving that purple one in the center, which is the atrium. So the atrium is going to be tackled next summer. They do have, and that looks like the main and only exit, but there's 6 other exits around the building, and so you do have to do alternative exit plans, because you can't exit through the lobby. So working with code consultants to get that organized. Dalhousie has interesting issues. Dalhousie has an aging workforce, as many organizations do, and so a whole lot of institutional knowledge within the people that are there. So how do you make sure that gets documented and into something that gets codified and something that people can refer to? And if someone comes along after the fact and says, okay, we're going to do another retrofit within this building to do something, whatever it is, they can refer back to something and say, oh, I understand it. Or maintenance personnel have an issue in the middle of the night and they have to understand what's going on with the building. You can say, oh, I understand it. So Very good process of documentation and documentation control for Dalhousie. They have all of these requirements. On day one, you have your basis of design. They do have design guidelines that are required by the consultant to sign off on. As you start the project, you do have a commissioning plan. You go through the commissioning phase by phase. Every 2 months, we move to another phase, and we do the commissioning for each of the spaces. When we do the TAB, testing, air adjustment, and balancing, the TAB report for each of the zones progressively as we move through. They have operations and maintenance manuals. They do have requirements of the contractor, MCW Custom Energy Solutions, the consultant, MCW consultants doing business as MCW AmeriCorps, and the contractors that we hire to do the work to get their maintenance documentation together, which is the FAMIS, famous equipment records, which is just a great maintenance program that they have to organize all of their information, record drawings, training plan and training manuals, and it can't just be anyone who trains people. You got to have properly qualified people, so you get the right people to do that. The systems operations manual, the functional performance testing to smoke out any of the issues that the building has, and the warranty plan and manual if there are things that need to be addressed after the fact. Okay, pre and post retrofit. So as you get into a building, you analyze it as you get going. So you do all the pre-retrofit measurements. So we looked at the lighting, we looked at the tab, we looked at motor testing, thermal imaging, plug loads. You go through each building. Oh, you have a coffee maker. How many cups of coffee do you have per day? So anyway, you got to figure all that stuff out. You get the trend logs. So we have all that stuff, and any testing to make sure that you know exactly what's in the building wherever problems may occur. On the measurement and verification side, we do have an energy performance guarantee on the project using the IPMVP, International Performance Measurement Verification Protocol. The guarantee on this one is structured that it's option C, which is the whole building, because Ray and the team have good meters on all of the main systems that we can use those. Although for incentive requirements, as well as just for good management of measures, there are some option A and option B for retrofit isolation. And that covers almost all of the savings. We identify all the static factors which could come into play. And the good thing about our partner at Dalhousie University is they have very realistic expectations about what is within our control and what might not be. And so anything that is problematic that could jeopardize the energy savings, they are reasonable people, and they say, yeah, we get it. Filters couldn't get loaded, and that can impact your energy. Other things like steam traps, they're going to be testing all the steam traps. They're going to be calibrating meters. So all of that good stuff. So, hey, sorry if we're going over the time. I could use this, perhaps.
Yeah, use that one.
And so the results, benefits, and next steps. So where do we get to? So yeah, interesting to hear some of what makes a deep energy retrofit. So yeah, 50%. So look at that, we're making 50% on each of those. Energy savings, 55. Energy cost savings, 53. Greenhouse gas, 52. And the resultant EUI is at 20 EKWH per square foot. So the benefits of the program, as we were saying and as Ray described, renewal of the systems, automation and control for better building control. And that's the big issue for all of the occupants, is knowing that they get good and proper ventilation. At the end of the day, as we go through, we do have air purifiers as we move space to space and interrupt their zones. Of course, efficiencies and energy efficiencies, advancement of climate change goals, and this, as you're doing your sales job and you say everything's about the ceiling, the air quality, the visual aesthetics, and occupant comfort, combined with duct sealing, strategic window replacement. There are some, failed sealed units. There are some cracked windows that are just difficult to access that Dalhousie hasn't been able to access. The atrium is extremely difficult to access. it's 80 feet up in the air, and it's, you know, you can't get a lift in there easily. So we're going to clean up all those windows, improve all the mullions as you go through the project, through the building, and so you end up with a nice finished product, a product that looks much better at the end of the day. So, where's Dalhousie going next? With MCW, we're looking at a number of things. We're at the Sexton campus to expand the geothermal system. Where's Aaron? Expand the geothermal system and recover energy from the lab exhaust system. At the Central Services building, we're going to put a boiler stack heat recovery system in, or we plan to. We're in the study phase of that now, and that's where I talked about the conversion of their chilled water, their dormant chilled water asset, to use that for a low temp hot water heating system. The chemistry building, short-term energy upgrades for now, as they develop out their bigger new building, and Dalhousie does have a plan to convert all of their buildings, the ones that make sense, from steam to hot water, and with a probable plan to convert over the long range time, their tunnel hot water heating system back to their Central Services building to be low temp hot water as well. So that's our presentation.
Hello? All right, we're going to get a mic change, but we'll just have to talk loud for our questions. It might wake us up a little bit. I would like to give some context. Thanks, Ted, for the shout out there on our night audit. So yeah, before Ray, I was energy manager at Dalhousie, and when MCW was preparing the first initial models of this building, I think they had predicted lights were on 12 or 16 hours a day. I can't remember the number. I just remember saying to Ted, I think your baseline's too low. These lights are on 24/7. And he said, I don't think they are. And I said, well, let's go do an audit at midnight then, and we'll prove it. And to Ted's credit, he was very open to it, and I think he was actually excited to do it because it made his project bigger in the end. So anyways, just thought I'd add that. A little bit of context. But if there's any questions, we have a few minutes, and then we'll move on to directly to the next presentation.
Hi.
Surprise, surprise, I have a question. Sorry, guys.
No, all good. This is great.
So I think that all the work you're doing is really great, and that was involved like one-line diagrams I've seen in years. So I appreciated that.
Is that good or bad?
No, it's good. It's
Okay.
good. I found it very interesting. I was just very curious about like the information sharing, like because I've toured like another net zero. Well, it's actually a net zero building, and it's an educational institution. And in the front they have screens that are updated in live time with like the energy that's consumed, and then like you said you're installing solar panels on the wall, right? Not the roof.
That was one of the options. Yeah, yeah. We're not proceeding with that right now, but yeah, yeah.
Okay.
Yeah.
Well, even if you did it with reference to baseline, because like especially being an educational institution, I think that's really cool. How people can kind of like see how the energy uses change, even if it's like cold weather outside. You know, to have that like in the front entranceway, I thought was really cool. And this other building I toured also had like the live solar panel like production as well. But I was just curious about like the information sharing aspect of it.
Fantastic.
I can touch on a little bit. We have tried that with the Emera IDEA building that was constructed. There was a screen in there to display like the live energy information. The problem with that is if there's an issue, it can really like make it seem worse or better than it's actually performing. And although we rely on our data and we trust the data, we don't have a chance to clean it up before it reaches the screen to be actually live data and useful data. So it would either require someone to like actively be monitoring it and maybe having a delay on what's shown on the screen, which costs resources and someone's time, or what we end up doing is just scrapping it. And I think I think there's still screens there maybe, but I think it's more weather data and like kind of just useful information, but less so on the building. So I appreciate, and I hear you too. Like for university, it's good to demonstrate like what we're doing. I just think there has to be another way of presenting that information. So maybe even like, hey, we could do it like a summary of like the past month we've saved this much energy or did this. That might be a good idea to build on. So thanks for the comment.
The other interesting thing is that normally this type of work does include an energy awareness campaign, but because the university does have such a strong Office of Sustainability, that they have said that, thank you MCW, we don't need you folks to do that. We're going to take care of that part ourselves because we already are fully quite engaged with all of the building users and people at the building. So there are other approaches that they use to engage with the users and students. So,
Yeah, thanks for that.
yeah.